Testing. 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 Tak nampak. Hey guys, finish? Siap tak? Denny? Okay. Hanif? Arif?
Dah.
Finish where's the others?
Madam tak lapar, madam?
Ha? Oh, tak lapar? Lapar sikit lah, sikit. Lapar sikit lah, minum air kosong dulu. Nanti makan. Nak habis, saya risau nak habiskan ni hari ni.
Madam boleh habiskan semua ni ke hari ni? Satu slide lah.
Boleh, insyaAllah. Sebab tu yang basic awal-awal kena faham, sebab masuk slide-slide seterusnya you tengok ada banyak equation kan?
Sebenarnya apa yang madam ajar tu ada kena-mengena sikit dengan madam yang apa tu?
Dr. Fiza.
Dr. Fiza.
Memang. Dr. Fiza ada ajar pasal mass tu kan? Sebab sekarang ni yang saya sambung adalah untuk damper dengan spring plus nanti response untuk kalau effect of damper dalam sistem. So dari situ kita akan buat mathematical modeling semualah. So means that nak plotting dalam MATLAB, tengok response semua and so on. So yang hari tu Dr. Fiza dia ajar untuk maths je kan dengan Indonesia kan? Ke dia ada masuk damper dengan spring?
Ada, semua ada.
Ada juga.
Oh ada juga. So saya boleh cepat lah ni?
Boleh.
Oh boleh cepat, okay. So misalnya saya risau yang tak ada background electrical ni. Okay. Alright. But everybody can follow my lecture kan? Boleh kan? Slow sangat lah maksudnya? Slow sangat ke maksudnya?
Tak, biasa je.
Biasa je. Okay. Tekan slow. Kalau slow saya cepatkan lagi. Saya rasa macam habis pula dah. Okay. One more. 7, 8, 9, ada 2 orang lagi. Ni kot. Iba. Zamzame dengan
Syadik.
Apa ni? Syadik. Okay, since just now some of you commented that you already learned it in the previous with Dr. Fiza kan? So then that's good. I will be very fast right now. So ada yang baru masuk ke?
Jadi.
So let's just do this equation. Find the equation. You have 2 mass. Okay, mass 2 is connected to K2 and K1. Then you have mass 1. You pull it, force value, then you have a displacement of x1 and x2. So first get the equation for M1, M2 value. So M2, okay, M2 is x2 double dot plus K2 x2 plus K1 x2, okay, equivalent to, you have any force here? No. So,
0.
Yeah, you don't have any force here, so it's equal to
0.
okay,
On the opposite, K1, X1.
K1, you have K1 connected to the x1 displacement.
X1.
So plus K1 x1. So this one you can write it as M2 x double dot plus, if you are going to write it in terms of x, x1, so x2, so you have K1 plus K2 x2 equivalent to K1 x1. So this one is the first equation. Okay. But if you want it to have the same equation like in the slide here, okay, so means that this is minus K1 x1 equal to 0. First equation. Okay, first equation. The second equation is at M1. So M1 x1 double dot plus K1 x1 plus, do you have anything else connected to M1? No. So no plus equivalent to F plus K1 is connected to E2. K1 x2. So you have M1 x1 dot plus K1 x1 minus K1 x2 equal to F. So this one is the second equation. Alright? So it's very simple, this one. Or if you want to make it in the same equation like in the slide, M1 x1 double dot plus K1 x1 minus x2. Okay? Oh. I think I missed out another one. M1 x1 K1 x1 equal to K1 x2. Okay? Equivalent to F. Okay? Okay, so now we go to the damping element. Damping element. Okay, that one just now was mass and spring. Now we go to damping. But before we go to damping element, is that I'm going to talk about friction. Okay, so what is friction? Actually, when you have a damping, then you have actually a friction. Why? Because when you have a friction, means that when an object is moving, then it's going to slow down the object motion. So that one we call as damping. Okay, so force that act opposite to the relative motion of two surfaces. So you have either dry or rough surface. So that's or you have smooth and wet surface. Okay, so let's say that you have this mass object M. So you apply the force in this direction. Then the opposite of this applied force is the friction force. Okay, so normally when you model this equation, you have a mass and then you have the base here. Normally we assume that the friction is 0. Okay, but in reality you have actually the damping value, okay, which is the friction force. Okay, and you have the normal force moving up and gravity is down there. Okay, so how to calculate for friction force is that you have Fs equal to Fn, which is the normal force, times nu s. Nu s is the coefficient of static friction. Okay. So what is actually static friction? So the force of static friction keeps the object at rest. So example, you have this duster. If you put it on the table, it's not moving because you have the static friction there. Okay, and in comparison is that you have the kinetic force or kinetic friction. So kinetic friction is something that that will slow down a moving object. Okay, so it means that, example, you are doing a simple experiment right now. You have a box, you try to pull it. You try to pull a box. Means that in the beginning that the box, between the box and the surface, you have the static friction. Okay, static friction. Then after you overcome the static friction, you have the kinetic friction. Okay, kinetic friction, which is when it starts to move. Okay, so this is the equation or the coefficient of static friction, nu s, and nu s for the kinetic friction. So if you see here is actually the friction between materials, okay, rubber on grass, if two, and so on. So if you see here, the largest friction is between rubber and concrete lah. You see here 1 or 0.1. The less is joints in human is much more less friction. If not, we are going to have pain every time. Even ice on ice is 0.1 and 0.03. Right? Just a little bit of introduction. Okay, just tap that one. So this one is just a bit of procedure how to actually measure a static friction. Okay, so you connect the wood block to a sensor, a force sensor. Okay, pull the force sensor, okay, gently to the right side until the unit begin to move. Okay, so means that you pull it until it start to move. So move the block slowly with constant force. So you move it until it start to slowly move it at the speed. So actually, when you do the experiment, is that what happens is that when you pull the force, it's actually constant here. This is we call a static region, and afterward it reached to the value of this static region maximum, you will have the kinetic region. Okay, so from here is that you can actually calculate what is nu s and nu k using this equation. Right? So this one is another way how to actually find out the friction coefficient by using a displacement sensor. Okay, so they are using the motion detector to actually detect the speed, okay, of the block, and then from there you can plot the result and then do some calculation, find the coefficient of friction. Right? So damping element, as you know, I think I will go very fast. You can read it. This description, and damping element is element that resists relative velocity across it. So example of damping element is this piston. Normally a piston you either use hydraulic inside or you have air. So the reaction force on the normal force will be the friction force. Another example of damping element is cylinder that you use in a door, close, open and close a door, or this one is the detail of this cylinder, and or in the shock absorber, okay, in the plane, okay, on the plane. So you have the piston, and normally this one you have using oil fluid. So let's do the modeling, very fast one. So we have two different, from now you already know that you are going to do both linear and rotary. Okay, so for linear is that we have mass, we have the K spring just now, and then we have the damping value, so FV. Sometimes we also use C, okay, C as a damping value, the coefficient. So F equal to FV dx over T, so we get F equal to FV dot V, because dx over dt is the velocity V. So we have this equation, and from here we can actually write out the transfer function. And from here, if you take out this numerator down here, so you find out this is the static equation. And from here, from the static equation, you see that this is actually a complex conjugate roots. So meaning that if you see that it's a complex root, means that it's a damped sinusoidal function, means that if you give an input, then it's going to have an oscillation before it settles down, okay, to the steady state. Okay. So let's go to this example. Okay, I'll go very fast. So you have mass K and C. So you have this equation, okay, M dot mx dot double dot plus b, or you use c here, cx dot plus kx. So you get its equation. From here you can actually rearrange it. You can get f equal to mxs. So you will get the transfer function for the system is input over output, which is 1 over ms squared plus cs plus k. So this one will be the equation, and the numerator part is the characteristic equation, okay, where you can see if it's going to have a damping value and so on. And this one will be the effect of gravity. So when you have the effect of gravity, you have the theta value. So similar to the mass spring value just now, so you can actually derive it. Then you get this equation, mv dot, okay, assuming that mx squared or mx double dot equal to mv dot, okay, so you get mv dot. Okay, it's the same lah. Okay, I just write it in a different way. So this one is in differential equation, this is in state space. So you have mv dot plus cv equal to md sin theta. Okay, for this transformation. Let's go to this slide, effect of damping. So we are going to see what is the effect of damping to a system. Suppose that system shows below m equal to 1, spring constant is 16. Okay, investigate the free response as we increase the damping for 4 cases. So C value is not given here. Okay, so C value is C equal to 0, 4, 8, 10. It asks you to actually get what is the response based on different C value. So given here the initial condition is x 0 is 1 and dx over dt is 0. Okay. So how to do this, to answer this question is that, okay, this is a graph, but before we go look at this graph, let's do the derivation first. So by using Laplace transform and property of Laplace, so you have learned with Dr. Norfiza about Laplace transform, right? So first of all, from this equation, okay, we continue here. So x double dot plus x dot plus 16x equal to 0. Then using the property of Laplace. So this one is the property of Laplace. Okay, so look at this. This is x double dot. So x double dot is this one. Okay, so substitute it s squared xs minus sx0 minus x dot at 0. Okay, plus c value, c x dot is this one. So x c s x minus x0, this one, plus 16x equal to 0. Okay, so now we substitute the value of initial condition x0 equal to 1 and x dot 0 equal to 0. Okay, so substitute that value. So you have x0, 1 and so on, blah blah blah. You substitute, you will get this equation. Okay, you can try to do it at home, get this equation. Then from here is that, get what is xs equal to c of what plus 1 over s over this value. And now is that, okay, look back at the cases that they gave to you. 4 cases of c equal to 0, 4, 8, 10. So let's do the first one for case c equal to 0. So if c equal to 0, substitute c here equal to 0. So you have s over s squared plus 16. Rearrange it as to become this equation. Okay, using this, refer to inverse Laplace. So inverse Laplace is this table. I took only for the value for cos omega t. So if you see this, compare with this equation. So it's actually representing cos omega t. So that's why you have the value xt equal to cos 4t, right? So do the rest. Okay, 4, 8, 10, substitute into this equation. Okay. Okay, sorry. So now, after doing that, okay, you will see that this is c equal to 0, c equal to 4, c equal to 8, and c equal to 10. Meaning that when you have no damping value, means that it's going to oscillate. Okay, much. When you have a value, damping value 4, 8, 10, it's going to oscillate, but it's going to go to equilibrium, to the equilibrium position at the same position for 6, 4, 8, 4, and 10. Okay, you see that for 4, 8, and 10 is going to the same equilibrium position. Okay, means that mass take longer to return to equilibrium because the damping force greatly slow down the mass. So for the case of C equal to 0, actually it's going down a bit here lah, a bit late lah. Okay. Okay, this one is another example. Another example, you have a system, you have mass, you have K1, K2, and then you have a damper. The damper is connected series with K1. Okay, don't panic. Okay, just look at the equation, try to do it similar as what you have did before. Okay, so first of all is that how to get this equation is that to write out the equation at M. M equal to mx double dot plus cx plus k2x blah 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 and so on lah. Okay, so you will get the first equation okay, with respect to the position of x. So next is to get with respect to displacement of y. So displacement of y, you have 6x dot, okay, minus 6y dot minus k1y equal to 0 because there's no force at this point. At this point, so you will have the second equation, ys equal to cs over k1 plus cs xs. So substitute this y into this equation, first equation, substitute it, you will get this equation. Okay, this one will be the final equation for x over fs because the question is that determine the transfer function xs over fs. Okay, everybody okay right now?
Okay.
Okay, everybody is so silent, so I'm not sure if I'm talking or anyone there. Okay, so next we go to this example. Okay, this is test yourself. Input, the input is displacement, output is the displacement x of mass. So you have m here. Okay, the difference is that you have x is the same point, but y you have at a different point. So you will get different and transfer function. So this one, just do it at home. Try to derive it. Okay. This one also try to do it at home. This is very similar to what I have drawn here. Okay. Just that you have the additional. Additional damper. Okay, you have the damper additional here. That's all. Okay, so just try to come up with the equation. Try to prove that you can get this equation. Okay. Okay. This one is on linear motion. Now is on rotary motion, translation motion. So similar lah. When this was example from undergraduate. So you have J1, J2, we have K connected in between, we have D1 dash point and D2. So find out what is theta 2 over Ts. So you can try to look at the example here given, how to get this equation. Then this equation, try to do it at home. Okay. And then if you have derive it, you can actually show it to me later on. Okay, and then this is an example when you have 3 inertia, J1, J2, J3. So find what is the equation for each of the equations. So basically you have three different equations based on theta 1, theta 2, and theta 3. Okay, very fast. And then this one is to show the effect of damper location and the numerator of the dynamics here. So let's go to see the first example. You have M, mass here. You have K and the damper connected to the same side, which is on the left side. Okay. So you have X displacement, Y is displacement here. In contrast to this second example is that you have mass, K is the left side and damper is the right side. So you're given all the value M, C, and K. So find out what is the unit step response for each specific. So what's the difference? What are the output that you will actually derive from these two systems? It looks like, but you will get different response. So the first one is that derive this, okay, get this equation, you will get, okay, you will get this one, This one is the equation that derives, so CS plus K over MS squared, blah, blah, blah. So substitute the value, substitute here, you will get this value, okay, and then using partial fraction, okay, remember partial fraction, so by using partial fraction you will get this equation, okay, and then you will need to use partial fraction, okay, and then from here is that use the Laplace transform to get what is the value for xt, because it asks you to plot what is the time response, so which is in time domain, okay, so xt is 1 over s is unit step, so 1 plus 1 over s plus 2, 1 over s plus 2 is this one, e minus a to t minus t minus 2 e minus 4t. So this is the equation for this block, right? Second equation is that when you have mass, k is on the left side, damper is on the right side. Get this equation, okay? Substitute value for m, c, and k. You will get this. Using partial fraction, you will get value for a, b, and c. Then using inverse Laplace, using the Laplace transform pair, you will get the value for xt. Okay, so let's see what's the effect of having two different setups. So you have two different setups. For the first case is that you have damper and k in the simple side, So you will see that for the numerator part here, numerator part, okay, you have ck plus k. But for the b part is that you only have k value on the numerator. So you see that the numerator causes an overshoot in the response but does not affect the steady state. So steady state means that in the end it will go to the same steady state value, okay? But this numerator will actually cause the system to have an overshoot, okay? The damper location can affect the response, so it's going to affect the response. You have a little overshoot, and damper location does not affect the time constant, means that it's not going to affect the steady state value. It's going to have the same steady value, but it's having the different settling time, okay? For k value, that doesn't have any overshoot, okay? So that's the difference. When you have two different systems, the location is really important, okay? So an energy method is, I skip this one because this one is not going to be in your final exam, Final exam, okay? Lastly is that MATLAB. So MATLAB function, MATLAB function, what is this? Okay, MATLAB. So this one is just a function. Those who already used MATLAB before, you already know what is the plot, TF, transfer function, and so on. Okay, let's see this example. So this example is, use the MATLAB step function to obtain a plot of free response of the model following model where x0 is equal to 4, x0 dot at 0 position is equal to 2. Okay, you are given this equation. This is the equation. Okay, so first of all, use the inverse Laplace transform. Okay, so write it as this: 5s squared ss 3sx plus 10x equal to 0. Then using the inverse Laplace, so you will get this value, substitute the value, substitute value for this value, then you will get this. Okay. The next is that after you substitute everything, okay, you can actually rearrange the equation, okay, and you will get this equation. Okay, this equation, rearrange it to become xs. So xs equal to 20s plus 24 over this equation. And then for the case of this equation is that you are given xs, okay, the aim is that to get the transfer function of a system. So you have x, given x here, x. So you have an output. Okay. So output is actually t is actually xs times ys. Macam salah je ni. Sorry So t y xs equal to t dot ys So you will get this equation. Okay. Sorry wait for a while. There's somebody at the door. Okay, sorry. Alright, so you get xs. So, but for this case is that you need to use the step input. Means that the input is step 1 over s. So if you refer to the Laplace transform, step input 1 is actually when you use Laplace is 1 over s. That's why you can write again this equation as ts times 1 over s. So this one sub times s over s. Okay, so you get s squared, 20s squared plus 24s times 1 over s. Okay, so what you need to do is that get the tf value. So tf value is actually transfer function of the system itself. So transfer function in MATLAB. Okay, now we are going to do the MATLAB exercise. So open MATLAB. Okay, you have an input system here. Okay, system equal to transfer function. So look at this transfer function. Create a model in transfer function form. Okay, so it means that we are going to actually come up with the transfer function of the system using this code. So TF20 is this value plus this one is not 22 sorry, 24 0 5 3s plus 10. Okay, and then step system is, look at this, step is compute plot time response of the linear, because the question was to actually plot step function. So step system, right? So if you do this equation, this exercise, you will actually get this graph. Means that this transfer function, the transfer function is given by this equation. Okay. Okay, so this one is exercise that you need to do at home. Okay, so determine the free response with MATLAB. So by referring to the previous slides, they find out, obtain the plot unit response of x2 for 0 initial condition, and B, use method MATLAB to obtain free response using x1. So first of all, let's get the equation for the system, and then after getting the equation, then substitute the value for initial position x0, okay, and this one, and then get the transfer function, and then using the coding here, code here, or you can use the same example here, plot the transfer function. Okay, so any question? That will be all for this part 1, spring and damper. Any question before we end the meeting?
Madam, Wednesday do we have session?
Tomorrow is for tomorrow morning. You want morning class or afternoon class?
Up to madam.
Afternoon class. Okay, like this. I'm planning to actually do our class this week 3 times. Means that one session for 1 chapter. So today is for part 1. Okay, tomorrow will be for the electric and electromechanical. And then the third one is Wednesday, will be on the thermal and fluid. Okay, so 3 days. So tomorrow, if you're okay with it, then I would say, wait, I check my calendar. Tomorrow afternoon, afternoon, class at 2. Is it okay?
I guess morning is better if you can morning.
Pardon?
If morning maybe is better.
Morning?
Yeah, if you
Who
can.
won morning class? Raise your hand. Morning
I'm okay.
class. Morning class.
I'm okay.
I'm okay.
I'm okay, raise your hand. I'm okay, raise your hand.
I don't mind.
3. Afternoon class. Raise your hand. Afternoon class.
So,
Itu tak ada pula, Danny. 4. If morning class, tomorrow slide, I think not much good. And I think I can, most of you have background in electrical, right?
yes.
Electrical, right? So I
Yes,
think
ma'am.
tomorrow, if we want to do morning class, since you guys, you don't have anything to do, right? If you don't wake up in the morning, then what you do in the morning? So we try to do the class at 9:30. Is it okay?
Okay.
9:30.
Yes.
9:30
No problem.
until finish. Maybe we finish at 1 or 12:30. Depends lah. Okay. So
Okay.
9:30 tomorrow. We meet again. I think using the same link lah. Okay, no problem
Okay.
Alright,
Yes.
so don't forget to do the MATLAB exercise
How
Alright,
about Wednesday, madam?
pardon?
Wednesday.
Wednesday. Wait Wednesday also same.
Morning.
Same.
9:30.
9:30. Okay?
Okay.
So
Okay.
I don't think for master student need to have like detailed class like undergraduate, right? Because you just can actually refer to additional references, not only on me talking like this. I think you get bored also, right? Okay. So last round table, not round table, round screen. Danny?
Yes, madam.
Yes,
I don't
madam.
have.
Any question?
I don't have question. I don't
No.
have question.
Hanif?
No, madam. Thank you.
Ahmad Arif?
No, madam. Thank you.
No, madam, thank you. Kugan.
No questions, madam.
Okay, Zamzame?
No question.
Okay, alright. Shadik?
No question.
Shadik, his view is from bird eye view, from the top part, Heba? Any questions?
Yes, you told us that we need to do the MATLAB. And do we need to submit the MATLAB for you?
Yes, you need to as assignment.
How
Do
to
the
submit
calculation
this?
means that for this exercise, make sure that you do the calculation. You don't need to do the using equation editor. Just write it out and then submit it. Hard copy is okay. Scan it, hard copy, scan that and email to me. Okay, my email is mariam@utem. Okay, Mariam.
When should we submit that?
You can submit it next week. Next week.
Okay.
Next week, Okay, so my
Okay,
email
madam.
is this one, mariam@utem.edu.my. Email it to me, the calculation and also the MATLAB response time. Lastly, who else? Ain?
No.
No.
Question.
Ain, okay?
No. Okay.
Okay, alright. So that be all. Thank you very much. See you tomorrow at 9:30.
Okay. Thank you,
Thank you,
madam.
madam.
Assalamualaikum.
Thank you, madam.
Thank you.
Salam.